So in the previous video, we looked at naming cycloalkanes, cis-trans isomerism, ring strain, conformations of cycloalkanes, how some of them are puckered, and then I introduced the chair conformation for cyclohexane. Now we're going to really focus in on cyclohexane in this video and look at the conformations of mono and disubstituted cyclohexanes, and then we'll finish up the chapter with polycyclic molecules. Cyclohexane, when it adopts the chair conformation, has no angle strain and no torsional strain. And this is what the chair conformation looks like. We could also draw it as a Newman projection if you're looking down these two bonds. In the last video, I introduced how you draw the chair conformation. This is something that will require practice. You should try using these 5 steps to draw your chair. If drawn correctly, the chair should contain 3 sets of parallel lines shown in red. And each carbon of the chair is going to have an axial substituent and an equatorial substituent. In drawing the axial substituents, those are the easiest. You're going to start by, in the right-hand corner, drawing a stick up. You're going to have an axial bond up on that carbon, and then it just alternates around the ring. So then the next one would be axial down, axial up, axial down, and so on. Then after you have the axial substituents drawn, you want to draw in the equatorial groups. Those are a little harder to draw. They're drawn off the ring and they run parallel to the lines in the chair. So on the carbon that you had the axial up, now you're going to have an equatorial down. Then on the next carbon where you had an axial down, you have a bond that's equatorial up. So notice the angle here is slightly down, the angle here is slightly up. So every carbon has an axial and an equatorial substituent, and if one is up, the other substituent is down. Now, if you have a substituent on your cyclohexane, so something other than just hydrogen, there are 2 possible chair conformations. This chair conformation, we'll call this A, and this chair conformation, we'll call this B. Now these chairs can interconvert via what's called a ring flip. So notice that the X group is axial up in the first chair, and here it's equatorial up. So when you do a ring flip, things that are up stay up, but whatever's axial becomes equatorial, and whatever is equatorial becomes axial. Now this is the movie that played in the last video, and this just shows a chair going through a ring flip and the different types of conformations it goes through on the way. But as a result, what was axial becomes equatorial, and what was equatorial becomes axial. So now it's ring flipping again, going through the different stages, and now it's back to the other chair. So the skill you're going to need to learn is how to draw the 2 different chairs and do a ring flip. So notice how this chair is kind of skewed in that direction to the right, and this chair is kind of skewed in the left direction. And then notice how this carbon with the methyl, Me is standing for methyl, is now that carbon. So I want you to just practice drawing both chairs. So if you draw one chair where you have axial and equatorial on every carbon, where this is 1, 2, 3, 4, 5, and 6. If I do the ring flip, then carbon 1 is now here. So this carbon is now down here after the ring flip. Now it turns out that if we're looking at these 2 different chairs, the one here with methyl in the equatorial position is a lot more stable, and methyl cyclohexane will exist in the chair 95% of the time. And the reason for that is that when methyl's in the axial position, there are steric interactions that destabilize that conformation. Now, the steric strain results from what are called 1,3 diaxial interactions. So the larger group, let's call it X, which could be methyl or something else, is going to bump into the other groups in the axial position. And if we represent this as a Newman projection, we can actually see that these are essentially gauche interactions. Just like we saw in the simpler Newman projections, it's the same type of steric clashing that's occurring here. But when the methyl group is equatorial, so like in this one, we don't have the steric clashing there. Larger groups will cause more steric crowding in the axial position. So this table shows us the energetic cost of those diaxial interactions and then the ratio of the equatorial to the axial conformer at equilibrium. So chlorine will exist mainly in the equatorial chair and a 7:30 ratio between it and the axial. Now notice how this number is going to be increasing as we go down this table. That's because this group gets bigger. So the bigger this group gets, the higher the energy cost for it being in the axial position due to those steric interactions. Therefore, the more it wants to be in that equatorial position. And then when you look at the equilibrium ratio, it's, for tert-butyl, this substituent, it's almost all in the equatorial position at any given time. What these numbers mean are that at equilibrium, for every one molecule where you have that group in the axial position, you have 9,999 with it in the equatorial position. Now, what about when we have more than one substituent on cyclohexane? Well, first we are going to need to interpret whether or not those groups are up or down. So with the solid wedge, that means the group is up, and with the hatched wedge, that means the group is down. So you want to first learn the skill of converting this representation into the chair. So if chlorine is up, if you place it on this carbon, the up position on that carbon is the axial up. So the chlorine would be axial up, and then the methyl has to be down, and the down position on the next carbon is axial down. And then when you do the ring flip, this carbon becomes that carbon, this carbon becomes this carbon. Notice everything that was axial becomes equatorial, but things that are up are still up. So this would be the equatorial up position. This would be the equatorial down position. Now see if you can draw both chair conformations for this molecule. So when you convert that to the chair, the ethyl, ET represents ethyl, ME methyl. The ethyl is going to be up, and if you put it at this corner, it would be axial up. And then the methyl will be down, and at that carbon, it would be equatorial down. Now you want to do the ring flip. So in the ring flip, this is going to make everything that was axial equatorial and vice versa. So when you draw your ring flipped chair, now carbon 1 is over here, and the ethyl that was axial up is now equatorial up, and the methyl that was equatorial down is now axial down. Now, which chair do you think is more stable? Go back and look at that table of values that are an indication of how big a substituent is. So think about this, which chair would be the more stable one, and then I will ask for your reasoning in class. The final topic is polycyclic systems. So decalin is the name for two 6-member rings fused together, and there's cis-decalin and trans-decalin. You can see where you get the names for these H's because they're both up in cis-decalin, but one's up and one's down in trans-decalin. The decalin substructure is found in many naturally occurring compounds such as steroids. And indeed, the structure of diamond is a network of 6-membered rings fused together. And that's it for this video.